In this problem, we are dealing with two tubes, both closed at one end. Now they vary in lengths. Now we do know that the longer tube means a longer wavelength, so a lower frequency. But really, the question's asking here that if we play high frequency notes or high harmonics on these tubes, there are times where they both resonate at the same time, but at lower frequencies we find that they do not resonate always at the same time. And the reason for that is basically that when we get into higher frequencies, there are more waves. So if we look at the bottom here, like for example F11, the 11th harmonic, we see that there are a bunch of waves. Now, because these tubes are different lengths, slightly different lengths, if there are more waves within the tube, there's a better likelihood that that they're gonna both end up resonating at the same time. But when we look at like the fundamental frequency F1 or F3, because of the longer wavelengths and not knowing the exact relationship between the lengths of the tube, there's not as great of a likelihood that they're going to both resonate at the same time. So basically, for low frequency sounds such as the fundamental and the third harmonic, the wavelengths in the tubes are longer. In other words, they're a large fraction of the tube length. As the frequency increases, the wavelength gets shorter, so there is a better likelihood that both tubes will resonate. Now, that's the physics behind it. Now, looking at just the setup and this explanation, for the AP test, we have a nice coherent paragraph here, complete thoughts, and also we included a few equations, V equals F lambda, and we show that F, the frequency, is proportional to the inverse of the wavelength, and we even drew a couple diagrams. So this is something that's good to keep in mind on the AP test. You can explain in sentences, but also include equations and diagrams just to kind of show the grader that you really understand your concepts. For 2A, we want to know the height at which the batter strikes the ball. Now, the problem tells us that the batter strikes the ball when the ball reaches its maximum height. So the ball is compressed on a spring, which is actually, when it's compressed, it's below the ground level, and then it's released at ground level, and then it goes up some height. So we can approach this problem a couple different ways. We can either use kinematics, or we can use energy, and I'm going to use energy here. So maximum height, so initially we have the potential, we got spring compression, so potential in the spring plus gravitational potential, and that's ultimately equal to the final energy, which is all gravitational potential. So we have 1/2 kx squared. The k is the spring constant times the compression of the spring. It's squared anyway, so it doesn't matter which way it's compressed, if it's compressed or stretched, 0.08 meters squared. And then plus mgh. Now notice how the h is negative 0.08 meters. That's because I set the potential gravitational to be 0 at ground level. So because it's below the ground, I'm going to define that as negative. And then ultimately that's equal to the mass times gravity times the final height. And again, that height represents the height above ground level, so that's 1.0 meters. Part B is broken up into 3 parts: the average force exerted on the ball by the bat, how long the ball is in flight after it has been hit, and how far the ball travels horizontally. So we're going to take a look at this now. Part 1 is an impulse problem. We know that impulse is a change in momentum. The ball is initially at the top of its motion right before it's struck. It's not moving, so its initial momentum pi is 0, but its final momentum is its mass times the velocity in which the ball comes off the bat, 30 meters per second. And we're trying to find the force exerted on the ball during a time of 4 times 10 to the negative 3 seconds. So that's the time in which the ball is in contact with the bat. So we go ahead and do our algebra and we solve for F, and that's 1,125 newtons. For part 2, we know that the initial angle is 0, so that means it's hit horizontally. So really this is a projectile motion problem, kind of like a ball being shot horizontally off of a cliff. So I separate my x and y. We have x, which is the horizontal motion. X is always independent of y. Whenever we're dealing with any vectors, x and y are always independent, including projectile motion. So we know that since the ball is struck 1 meter above the ground, that means it's going to fall -1 meters, so that's our delta x there on the right side. We know that the initial velocity in the vertical direction is 0. We know the acceleration of gravity is -9.8, or if you wanted to use -10, that's perfectly acceptable as well. And we're trying to solve for the time. Now, we don't know the horizontal distance yet, so we cannot use the x side yet. We have to look at the y. So we look at our kinematics equations. Delta x is equal to v naught t plus 1/2 at squared, and we get a time of 0.45 seconds. Now for part 3, we want to know the range or the horizontal distance. Well, in the x direction, there is no gravity. When you think about horizontal motion, gravity only acts vertically. So that means this is a constant speed equation. Distance equals the horizontal speed of 30 meters per second. And we know it's in the air for 0.45 seconds, giving us a distance of 13.5 meters. Part C is asking us if the ball failed to be released from the spring, so it's basically launched, but it sticks to the spring, so it causes it to oscillate. With what frequency would it oscillate up and down, back and forth? So really we have to look at, we know the equation for the period of a spring, which is 2 pi square root of mass of your object on the end of the spring over the spring constant K. So we plug in our values. We know the mass is 0.15 kilograms. We know the spring constant is 500 newtons per meter. And we get a period or a time of 0.11 seconds. So that's how long it takes for this spring to oscillate up and down one time. So we know that frequency is the inverse of the period. So 1 over 0.11 seconds gives us a frequency of 9.2 hertz. Free response question number 3 is a dynamics problem from Unit 3. So we have two masses on each side of a ramp, and they're connected by a pulley, so they're connected by the same string. So first thing I do before I solve for any of the parts here is I drew a free body diagram on each of the masses. So the mass on the left, we got the force of gravity down, we got the normal force always perpendicular to your surface, and we got the tension in the rope acting up and to the right. Now similarly for the mass on the right side, we got force of gravity down, a different force of gravity because different mass, normal force perpendicular to the surface, and again tension in the rope, and the two tensions are the same. So to solve for the acceleration of the blocks once they are released, we have to look at this as a system. So I can kind of see in my free body diagram, I already crossed out a few vectors. My tensions cancel out because it's the same rope, the same tension. I also know that the normal force cancels out with my perpendicular force of gravity. So the force of gravity, when I decompose it into the perpendicular and parallel to the ramp, again, that normal force cancels out with that perpendicular force. So really all I am left with is the parallel force down the ramp, the force of gravity down the ramp. So I have the force of gravity parallel of my big mass, M, capital M, minus the force of gravity of parallel, again, of my little mass, M, and that's equal to the mass of the whole system because both blocks are accelerating at an acceleration A. So Fg parallel capital M is capital Mg sine theta, and I'm going to subtract that from little mg sine theta. Now, why is one negative and the other is positive? Well, you can just define whichever one you want. So I said that that accelerating down the left side there is going to be positive, and then the opposite is true is for the right side. And then again, the total mass of the two. So when I plug in my values, or I'm given known values, I find an acceleration of 5.4 meters per second squared. Now for these problems, just as a quick check, anytime you're dealing with these kind of acceleration problems, ramp, pulley, anything like that, your acceleration should never be bigger than 9.8 because it's not going to accelerate quicker than gravity itself. So just keep that in mind. Part B is a little bit tricky, so really the question's asking us what is the force on the peg. Now the only thing in contact with the peg is the tension from the rope. Now if we draw a free body diagram, if you could see here kind of on the bottom right of this screen, there are technically two tensions, one acting to the right and down, and the other down and to the left. Now they're the same in magnitude, again because it's the same rope, but because of those angles are different, that means that the force is not going to be exactly just the tension in the rope. So first, let's find the tension. I'm going to choose one mass, because if I look at the system as a whole, the tensions cancel out like we saw in the previous problem. So I'm going to look at the big mass, capital M, which is on the left side of our diagram. So we know that Fg parallel acts down the ramp, we have tension acting up the ramp, and we know that the big mass is obviously going to, well, I shouldn't say obviously, but it's going to be greater than the force of gravity from the little mass as we saw in the previous problem. So it's going to accelerate down down the left side of the ramp. So we can see that 8 times 9.8 sine of 60, which is your force of gravity parallel, minus the tension, since they're opposite directions, equals 8 times 5.4, and again that 5.4 is the acceleration that we calculated in the previous problem. So we go ahead and do our math, and we see that it's 24.7 newtons. Now, again, because the tension is 24.7, well, the tension on both sides of the peg are not at the same angle, so they don't necessarily cancel each other out. Plus, they're both acting downwards, so those two vectors are going to add together. So really what we have to do is we have to decompose these two tension vectors and solve for x and solve for y. So if we look at x, we got 24.7 sine of 30 degrees with the vertical, so that's the x component, and I'm going to call that negative since it's to the left, plus, since it's to the right, 24.7 sine of 45, and that's equal to 5.1 newtons to the right because it comes out positive. Now same thing for y, except now y I'm going to use cosine, because again I'm measuring the angle from the vertical. So looking at my diagram, the cosine is the adjacent side there, which is the y component. So 24.7 cosine of 30 plus 24.7 cosine of 45, I'm going to call the downwards direction positive here, equals 38.9 newtons. Now once we have our x and our y, to find that net or total force, we have to use Pythagorean's theorem. A squared plus b squared equals c squared, and we see that that comes out to be 39.2 newtons. So that's the total force acting on the peg. Due to limitations on time for these videos, go ahead and click on the next video to see the rest of this problem.